Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to talk about graphs. In previous lectures, we've discussed a data structure called a tree. Today, we're going to look at something that's similar to them called a graph. Now, graphs are mathematical structures that's used to model pairwise relationships between abstract objects. More formally, graphs are a set of vertices and edges. We can say that a graph G is composed of vertices and edges, V and E respectively, where V, the vertices, is a set of all vertices V sub I. And edges are a set, E of K, that equals a pairwise or an ordered set going from a vertex Vi to a vertex Vj. Now the edges in a graph could either be directed or undirected. Directed arrows mean there is a one-way connection, so you can't go backwards. Undirected is bidirectional. What we can see to the right here is a directed graph. The big element to remember about graphs is they are a way to establish relationships between objects. The arrows, the edges, are the relationships, and that's going to come up a lot. Now, as mentioned before, we've already taken a look at trees, which do have a given structure. Binary search trees definitely have a predefined structure, and the same thing for heaps. However, graphs do not have a given structure. The data in a graph may not be comparable. In a graph, unlike a tree, you can have cycles. And this is a good point to bring up that all trees are examples of graphs, but not all graphs are examples of trees. So the structure of a graph is usually dependent on the problem being solved. We use these graph structures to represent these abstract objects and their relationships. Vertices may be considered as the abstract object, and the edges may be considered the relationship between those objects. In addition to that, edges may have what's called a weight value associated with them. One of the easiest versions of a graph to understand is a map. Think of it this way. The abstract object in a map are cities. They can be considered vertices. The edges can correspond to the distance between those cities. That is the relationship from one city to another. And in addition to that, finding shortest paths or finding a path at all is a classic problem that can be solved using a graph data structure. Now, there are three popular ways in order to implement a graph. First is called an adjacency matrix, then an adjacency list, in other words, that's the linked structure, and also an incidence matrix. Today, we're going to examine an adjacency matrix. The way that we represent a graph using an adjacency matrix is as follows. The rows and the columns represent the vertices. So for example, if the graph had n nodes or vertices, I'm going to interchange those terms a lot. If they have n nodes or vertices, then the matrix will be n by n. In our example, we had 7 vertices, and over here in our adjacency matrix, you can see that it is 7 by 7. Now the key understanding on how an adjacency matrix works is we map rows are the from vertex and columns are the to vertex. So the way that you could read this is from vertex V1 to vertex V2, there is a connection. Non-zero values that's stored in this matrix represent there is an edge and their weights. The version that we see over here is sometimes referred to as a binary adjacency matrix, where a 0 indicates there is no edge and 1 indicates there exists an edge. However, those values that are not 0 could really be anything. They could be distances, they could be whatever. Applying that to our previous example, we can see that the graph on the left is the adjacency matrix on the right. Going from vertex V1 to vertex V2, there is a directed edge. It exists. Going from vertex V1 to vertex V3, there is no edge. As you can see, V1 does not have an outgoing edge to V3. The key element is recognizing that in the adjacency matrix, if you have a non-zero value, that indicates an edge. And the rows correspond to the from vertex, and the columns correspond to the to vertex. Let's start implementing this. As you can see here, we already have our project ready to go, and we've already created our class Adjacency Matrix Graph. From there, we're going to define some properties that's going to be used in this Adjacency Matrix Graph. First of all, since we're going to base this on a matrix, in other words, a multi-dimensional array, we usually need some sort of default vertex count. So we create public static final int default vertex count, and we'll just set it to 10. By default, it's going to contain 10 vertices. From here, we now define our adjacency matrix. Private. Now we need to think of the type that this adjacency matrix is going to be. Well, the thing is, it's not really any kind of object. The things that's stored in the adjacency matrix is simply these numeric values that represent the connections. So this means we could easily choose like integer values, Boolean values, or in this case, we're going to use doubles. And this is going to be a two-dimensional array of type double that we're going to call the ADJ matrix. Next, let's create some constructors. Public ADJ matrix graph, create our default constructor, leave a little space, and just like before, we're going to kind of set this up in a very similar way that we've done array-based implementations of these data structures. We should give programmers the ability to establish the number of vertices that are in this. So our parameterized constructor is going to contain public ADJ matrix graph of some sort of size. And no surprising, we're going to now create a private void init int size that the two different constructors are going to call. To make sure that we do this, let's go ahead and call init from here using the default vertex count. And inside of here, calling init with the size. Now we have to establish if that size parameter is correct. We need at least one vertex in this graph. So I would say if this size was less than or equal to 0, that's not exactly correct. So let's go ahead and recall init using the default vert count to at least construct this adjacency matrix. And after that, let's return. Now, assuming that that size was valid, the next thing that we have to do is construct the adjacency matrix. ADJ matrix is equal to new double of size by size. Now, just to be safe, we want to establish initially that all of the values in this adjacency matrix are 0. We're going to add edges later, but for now, let's make sure that every element in this graph is 0. So for int I is equal to 0, I is less than ADJ matrix.length I++. Now that for loop only takes care of one dimension. This is a two-dimensional array, so that means we need for int j is equal to 0. J is less than ADJ matrix.length j++. Now we can sufficiently do this because we assume that the adjacency matrix is square. So that means this size is always equal to that size. But if we want to be extra careful, we may want to index into I. In Java, arrays are object types, and multidimensional arrays indicate that it is an array of other arrays. The outer arrays contain the references to the other arrays, and this is how we can index into these individual arrays. Now, let's go ahead and set ADJ matrix at index I, at index j, we need both, is equal to 0. So now this is the first part of how we can create this adjacency matrix representation of a graph. Now, in every other data structure that we went over, the next things that we talked about were how we add elements and how we remove elements. But a graph doesn't really do that. The graph is meant to model a problem. You're supposed to abstract vertices as those objects and then establish those pairwise relationships using edges. In fact, by constructing the graph, we've already created all of the vertices that we need. Now, an adjacency matrix that is implemented using an array automatically means that we cannot add or remove vertices from this graph. This is an excellent way to represent what's called a static graph. However, as we can't add and remove vertices, the thing that we have to concern ourselves with is how we can add edges. Let's go ahead and create the method public void add edge. Now what we're going to pass in is the indices. The first one that we're going to create is the int from vertex. Then we need an int to vertex, and finally a double weight. Now we know that a matrix or an array has a fixed bound. We need to verify if either of these indices are correct, if they are valid. This feels like a separate action. This feels like it should be a separate method. I'm going to enter down below here and create a private boolean is valid with an int index. Now we can verify this by returning this index is greater than or equal to 0, because all indices start there, and the index is strictly less than the adj matrix.length. If both of those are true, then these indices are valid. So inside of here, if not is valid from vertex or not is valid to vertex, then we have to return. These indices were not correct, either this one or this one, so we can't add an edge to something that doesn't exist. Yet, if both of those are correct, then all we need to do is assign the weight to the indices indicated here. So now we need to assign this weight. Let's take the adj matrix at this index, but which one are we going to correspond to? It really doesn't matter as long as you stay consistent. So let's go ahead and say that the first index corresponds to the from vertex, and the second one corresponds to the to vertex. And all we need to do to add this edge is assign the weight. We're about to start using this adjacency matrix graph in a minute, but before we do that, let's go ahead and write a print method. That way we can go ahead and verify if this is working correctly. The print method basically doesn't change, and the only thing that does change is that it's now a multidimensional matrix. So it's just going to look something like this. In order to test this out, let's go ahead and create a new class, and we'll call it the adj matrix tester. And let's include our main method. Now inside of here, what we're going to do is basically create the exact same thing that we have in our examples. So we create an adj matrix graph, and let's just call it graph, and construct it as a new adj matrix graph with the size being 7. So now we've sufficiently added all the vertices inside of this graph just by constructing it. Now what we need to do is establish the edges. There is a key difference from what we're doing from what is in the example. In the example, we started at vertex v1. However, in this one, consider v1 as being 0. So in other words, for every one of these, just basically take what you saw inside of the graph representation and subtract 1 from those values. So one of the first things that we had was from vertex v1, we had an edge going to v2. In this case, it corresponds to vertex v0 going to v1. So we call graph.addEdge going from 0 to 1 with a weight of 1.0. Let's go ahead and add all of the edges from this vertex 0. The next one from vertex 0 pointed to vertex 3. So adding this edge, we go from vertex 0 to vertex 3. Now let's go ahead and add the rest in. Now from here, let's see our adjacency matrix. Graph.print adjacency matrix. Running this. This looks exactly like the adjacency matrix that was in the slides. That's how we can set up a graph and how we can create those abstract objects, the vertices, and their relationships, the edges. But what can you do with these graphs? One important function in a graph is being able to travel through that graph structure systematically. This is commonly referred to as a traversal. Traversals can be used to search the graph, find paths, or detect features of a graph such as cycles. Now there are some common graph traversals. One of them is called depth first search, DFS, and it is based on a stack. The other one is called breadth first search, BFS, and it's based on a queue. Now, relating this back to a previous lecture, depth first search was a way that we traversed a tree. The thing is, pre-order, in-order, and post-order traversals were all examples of depth first search. Now, let's see how that applies to this graph. Now, in this version of a depth first search algorithm, we cannot assume that there are no cycles in this graph. A graph is allowed to have cycles, and as we can see over here, there are several cycles in this graph. So unlike the tree version, what we need to do is first establish that each one of the identifiers is unique. So in other words, vertex v1, v2, v3, all of the vertices have to have some sort of unique name. And along with that, we'll have a list of what we call the marked vertices to keep track of which vertices that we have already traveled to. The main idea of any depth first search algorithm is we're going to keep following a path until we reach a dead end. And then what we do is backtrack and then try a different path. So first what we do is we start from an arbitrary vertex. We can start from v1, v5, v4, wherever. Now once you've picked that vertex, add the vertices identifier to the marked vertice list. Then we have to follow some outgoing edge. If that vertex is already a part of the marked list, then we need to backtrack to that previous vertex. But otherwise, we keep repeating step 2 until there are no more reachable nodes. Let's see an example of how this works. Over to the left, we have our graph, and to the right, we have the adjacency matrix representation of the graph. Below that, we have our marked list. Let's assume that we start from vertex v1. If we start here in the graph, we also start here in the adjacency matrix. Now the first step, after we've picked the arbitrary vertex, is we have to add that identifier to our marked list. So notice that we're going to go ahead and mark that vertex and add it to our list. Now what we're going to do is systematically go from this vertex to these other vertices one at a time. As long as the value is non-zero, we understand there is an edge there. So let's examine from vertex v1 to vertex v1. There is no outgoing edge. And we could see that here. We don't have an edge connecting v1 with v1. So we move on. v2 is a non-zero value that indicates there is an edge going from v1 to v2. This means we need to travel along that path. Now we've traveled that path. v2 was not a part of our marked list, so next we need to add it to it. Now we need to repeat the exact same process that we did in v1. We have to find that outgoing edge. As we can see, going from v2 to v1, well, there isn't an edge connecting here to here, so that's 0. From v2 to v2, there's no edge. From v2 to v3, well, there's also no edge. However, from V2 to V4, there is. So that means we need to travel there. And V4 is not part of our marked list. So then we add it to our marked list. Now we got to find the next outgoing edge, which happens to be V3. So we travel to there. Now once again, we add V3 to our marked list and we try to find the first outgoing edge. We can see that the outgoing edge from V3 to V1 exists. But we don't travel there because V1 is already in our marked list. If we didn't do this, we may end up in an infinite cycle. This means we ignore V1 and we try to find the next outgoing edge, which happens to be V5. And so we travel to there. Now we've marked vertex V5. We need to find the next outgoing edge, which happens to be vertex V6. Then we add that vertex to our marked list. But notice, there is no outgoing edge in V6 at all. In essence, we've reached a dead end. And so now what we have to do is backtrack. Backtracking generally means that we're going to use a stack-based implementation. So the way you can think about this is we're going to pop that off the stack and then return back from where we came from, which was V5. Now we haven't checked all of the edges going out from V5, which there happens to be one more. V5 does point to V7. V7 is not a part of our marked list, so now we mark it. And just like V6, V7 has no outgoing edges. As this is a dead end, we now backtrack V5. Now we've exhausted all of the edges from V5, so now we have to backtrack again, this time to V3. Now starting back from V3, we check V6. V6 is already in our marked list. There is no outgoing edge connecting V3 to V7, so now we're done with V3, so we backtrack to V4. Now there isn't a connection V4 to V4, there is a connection V4 to V5, but V5 is already part of our marked list, so we're done with V4 and we backtrack again. There's no more outgoing edges from V2, so we're done with V2 and backtrack to V1. Now V1 has no connection to V3. V1 only has another connection to V4, which is already part of our marked list, and this means we're done. Another thing that this marked list represents is all of the reachable nodes starting from V1. Now, as just a quick example, if we were to pick another vertex, we wouldn't have the same marked list. And in fact, we may not have all of the vertices in our marked list. For example, if we started from vertex V5, V5 only has two outgoing edges. So its marked list would be V5, V6, backtrack, V7, backtrack, and done. There is no way, starting from V5, that we can reach V1, 2, 4, or 3. Now, let's implement this depth-first search traversal. Entering down just slightly, the way that we're going to implement this depth-first search is we're going to print out the indice values. In other words, the marked list. Now, it was mentioned before, depth-first search is based on a stack implementation. And we know that every time we call methods, those methods are pushed onto the call stack. In essence, what we can do is utilize recursion in order to develop this very simply. We're going to go ahead and create a public void print DFS. One of the critical elements in this depth-first search algorithm is we had to keep track of all of the nodes that we have marked. So this indicates that we might need another data structure to keep track of those. Now we don't exactly know how many vertices that we're going to arrive to, so we may need a resizable data structure. Well, why not use a linked list? Let's define it. Scrolling all the way back to the top, what we could do is use our general linked list, but for time's sake, let's go ahead and import java.util.star. From here, we can now create a private linked list of type integer. We're going to use an integer because the indices correspond to the unique identifier of each vertex. Now this linked list is going to be called our marked list. Before we use this, we do need to construct it. Inside of our initialization method, let's go ahead and construct the marked list equals to new linked list of type integer. Now using this, let's scroll all the way back to our printDFS method. The first thing that we want to do is make sure our marked list is clear. We may reuse this in a different algorithm. Now what we're going to do is use recursion, and we're going to do just like we did before and separate the recursive method from the callable method. So entering down, we're going to create a private void print DFS starting from some int index. From our public printDFS method, let's say that we arbitrarily pick vertex 0. So print DFS from 0. So now, once we have arrived at this vertex, what we're going to do is system.out.println the index. Which vertex are we currently at? Now that we have arrived at this vertex, we have to add it to our marked list. So, marked list.add the index. Now what we need to do is go from this given index to all of the other vertices that have an edge. So what we're going to do is create for int I is equal to 0. I is less than Adjacency I++. So now inside of here, if there is an edge, so if Adjacency Matrix at this index, going from this index to this index I, and that is not equal to 0, that means there exists an edge. And also, not marked list dot contains this index I. So if there exists an edge and it's not already part of our marked list, let's travel to this I. So this is where we call print DFS starting from that I. And because we're using recursion, this inherently makes this stack based. Every time we travel to a different vertex, once we reach a dead end, popping that method off the stack backtracks to a previous location. And this is depth first search. Let's see if it works. Going over here, we're going to call graph.printDFS. Looking at our result, it matches what was in the example. Now the other traversal algorithm is called breadth first search, and this works like the tree version of it as well. Now what we're going to do is assume that each vertex once again has some sort of unique identifier. We also have that list of marked vertices, and also we keep track of a queue of vertices. The way that breadth first search works is we add each one of the neighbors to this queue and then process them first in, first out order until we've exhausted all of the elements in the queue. In other words, we've traversed to the breadth first before going any deeper in the graph. More specifically, we start from an arbitrary vertex just like before. We add the vertex's identifier to the marked vertices list and to the vertex queue. We then immediately dequeue a vertex. We then enqueue all outgoing edges from that vertex as long as the vertex is not already in the queue or the marked list. Once we have done that, we follow an outgoing edge, and then we repeat step 3 until the queue is completely empty. Now seeing this in practice, we once again have the same graph and the same adjacency matrix. Below here, we have the marked list and the vertex queue. Let's assume that we start from vertex V1. Starting from vertex V1, we go ahead and we add it to both the marked list and our vertex queue. Now after we've added this to the marked list and the vertex queue, we immediately dequeue the vertex queue. Doing this, what we do is add all of its neighbors to the queue. So let's dequeue V1. Now we add its neighbors, the outgoing edges. In other words, values that are not 0, which is vertex 2 and 4. These get added to the queue. So now that we've added this to the queue, we can traverse to vertex V2 DQ it, add that to our marked list, and then add from V2 its neighbors, which is already V4. V4 is already in the vertex Q, so we don't re-add it. Now what we're going to do is DQ vertex V4, add that to our marked list, and then add all of the outgoing edges from vertex V4, which happens to be vertex 3 and 5. Now we travel to vertex V3, we DQ that and add it to our marked list, and then we add all of the outgoing edges from vertex V3. We have vertex V1, V5, and V6. However, vertex V1 is already marked, so we don't re-add it. We only add V5 and V6. Now we travel to V5. We DQ it and add it to our marked list. Then we add the outgoing edges from V5, which is V6 and 7. Next we travel to V6. We DQ that and mark it. There's no outgoing edges. But remember, this is Q-based. It's not stack-based, so we're not backtracking here. We're just following everything that's in our vertex Q. So what's left in our vertex Q is vertex 7. So we DQ that and mark it, and we're done. There's no more elements that have been added to this vertex Q. The vertex Q is empty, and therefore, this is our breadth first search. Let's implement this. Scrolling down a little bit, we're going to go ahead and just create one method. We're not going to use recursion because this isn't stack-based, it's queue-based. So we're going to go ahead and create a public void print BFS. Now the critical element of this breadth first search is it assumed it had two other data structures that it used. First was a marked list, which, well, we already have that. We also had to keep track of a vertex Q. Well, let's create a vertex Q. Scrolling all the way back to the top, we're going to create a private Q of type integer. And we'll just call it the VQ. Now, just like this marked list, we have to construct this VQ before we ever use it. We always want to avoid null pointer exceptions. Going down to our initialization method, we have to initialize VQ is equal to something. Now, there's a little bit of subtlety here, because the Q structure that's built into Java util is considered an interface. Remember, you cannot construct an interface. You can only construct classes that implement the interface. So in this case, while we cannot construct a queue directly, what we can construct is another linked list. New linked list of type integer, and we're good. Scrolling down to print BFS, let's go ahead and start. Just like before, we're going to call marked list.clear. We want to make sure there is not other data left over from a different algorithm, so we need to clear it out. And similarly, we're going to call vq.clear just to ensure that they're both empty initially. Now, let's pick the arbitrary vertex to start from. And just like before, let's start from indices 0, vertex 0. So, what we need to do first is our marked list, we need to add that element. Starting from here, we have to mark it. Similarly, we have to add it to our queue. And then, just to make sure, we're going to call system.out.println 0. Now, all we have to do is dequeue elements from the queue, enqueue its neighbors, and continue to do this while not vq.isEmpty. So while this vertex queue isn't empty, we just keep running that procedure. So let's go ahead and establish that the int current index, current I, is equal to vq.remove. Add is enqueue and remove is dequeue respectively. Once we have removed that from our vertex queue, we need to add it to our marked list. Marked list.add the current index. What we need to do now is systematically add all of the outgoing edges from this current index. So for int I is equal to 0, I is less than adj matrix dot length I++. So first of all, if not marked list dot contains I. So the index I that's being examined is not in our marked list. And not VQ dot contains this index I. It cannot be in either the marked list or the vertex Q. And we need to establish whether or not a connection even exists. So adj matrix from this current I to this index I, and that is not equal to 0. So this vertex, represented by this index I, is not part of the marked list, is not part of the vertex Q, and it has a non-zero value that indicates there is an edge going from this current index to this index I. Now, what we're going to do is, in this case, system.out.println this index I. And from there, vq.add I. And this is the breadth first search for a graph. Let's go ahead and test it out. Going back to here, graph.print_bfs. Running this is where the BFS is, and sure enough, it matches our example. Now, one consideration about this example is the depth first search and the breadth first search have the same values. This is a rare occurrence, and generally they don't have that. And this is only based on the structure of this graph. Now, graphs are a very important data structure, and they are incredibly useful for modeling a lot of problems. Being able to take a problem and then use the vertices to model abstract objects and then their relationships being edges, you can solve many problems using a graph. An adjacency matrix is only one representation of a graph. With all that being said, I'll see you next time.